So let's continue on with page 2. So this top part is the other way I might ask a question about intermolecular forces. And here we're talking about exhibited. And notice the word all here. So you're not really going to change your thinking. We're just going to explicitly state all of the intermolecular forces as opposed to only the strongest force. So if we look at our first example here, there's no hydrogens, so it can't hydrogen bond. We've got no lone pairs on the central atom, and the central atom here is bonded only to fluorine. So this is a non-polar molecule. And so since it's nonpolar, it only does dispersion forces. And so this is not anything different than what we talked about on page 1. Nonpolar molecules only do dispersion forces. But if we look at our next molecule here, it has a hydrogen, and that hydrogen is bonded to oxygen. So those are the two components for hydrogen bonding. But what we want to state on this page, and you want to be careful about how the question is asked, if something is hydrogen, can hydrogen bond, it can do dipole-dipole forces, right? Notice this is a polar molecule. It's got lone pairs on the central atom, it's bonded to hydrogen and chlorine. And again, everything, absolutely everything has dispersion forces, because all you need for dispersion forces is an electron cloud. So if we carry that thinking to our other examples here, no hydrogen, so it can't hydrogen bond, but quickly we recognize that there's lone pairs on the central atom, and so that makes this polar. Those lone pairs ruin that symmetry. So this can do dipole-dipole forces. And again, if something's polar, it does dipole-dipole forces, but that just adds to the dispersion forces that it also has. So again, it's not that it's one or the other, it's that it's both, right? We're layering on top of dispersion forces, dipole-dipole forces, and potentially hydrogen bonding. Let's look at our last example. So right away, you see that there's hydrogens here. So that's good, but what are those hydrogens bonded to? They're bonded to carbon. And so that does not fit hydrogen bonding. So again, not all hydrogens can hydrogen bond. However, one of the things that you might realize is that my carbon here, my central atom, is bonded to hydrogen and chlorine. That one chlorine ruins the symmetry. That makes this a polar molecule. And so just like C, it does both dipole-dipole and dispersion forces. So just be careful with the way the question is asked. So at the bottom of the page here, I want to start thinking about our phase changes, right? And so when we think about our phase changes, we've got gas to liquid. So we call it condensation. We can turn a gas into a solid. That's what we call deposition. And we can turn a solid, or a liquid I should say, into a solid. That's what we call freezing. And then the opposite of those processes, right? A liquid to a gas is called vaporization. A solid to a gas is called sublimation. And a solid to a liquid is called melting. So what we want to think about here is not only the process, but what's happening in the energy associated with these processes, particularly the particle motion. So the first thing you want to do is recognize your phases. Here we have a liquid, right? Particles close together, but not super organized. This is a solid. Particles organized together. This is also a solid. And then, of course, when the particles are taking up their container, that's a gas. And so liquid to solid, we know that that's freezing. Solid to gas, of course, is what's called sublimation. This is carbon dioxide, which you saw in lab 3. But let's think about the particle motion, right? In a solid, those particles have the least energy. A gas always has the most energy. And the liquid has kind of an intermediate energy. And so what we want to start thinking about is the temperature at which these phase changes occur is due to an interplay between the strength of the intermolecular forces that holds those molecules together and the amount of energy they have, right? In a gas, they have so much energy that they overcome any of the intermolecular forces. They don't stick together at all. In a solid, the strength of the intermolecular forces is so strong that it basically overtakes the energy. It doesn't allow those particles to translate, move from place to place. And so if we think about the particle energy, right, here in our first example, when we're going from kind of an intermittent energy to less energy, we are decreasing the energy. Where is that energy going? Well, that energy is released to the surroundings. That's what we call exothermic, right? So anytime you have something with more energy becoming a phase with less energy, those are exothermic processes. So condensation, deposition, freezing, all lower the particle energy. And the energy that's released comes from the stability that comes by seeing an increase in the intermolecular force strength. Whereas in sublimation, you're increasing energy going from a solid to a gas. Where did that energy come from? The surroundings are supply the energy here. And so you are bringing energy in from the surroundings. And so that's what we call an endothermic process. And so any of the three phases that lead to an increase in energy are endothermic processes. And so again, there's an energy flow that happens even in physical changes. And we want to think about that process and how that relates to intermolecular forces. It's something that you're going to, again, see as you do your balloon lab number 3. All right, let's move on to ranking boiling points.